Hi, and welcome to the next lecture unit in the lecture chapter on Gaussian processes, where the lecture unit is also called Gaussian processes, and where I will define the basic mathematical structure of GPs and how to work with them. I won't really talk about how to do estimation, or mainly define how we can mathematically work with distributions over complete function spaces. Okay, so until now, we have done something that some people call the weight space perspective. And this weight space view is something that's super common and that's nearly always used for any type of classical machine learning model. So we have considered hypothesis spaces, and these hypothesis spaces, they consist of functions, right? And we really want to learn about what's like the best function that matches our data the best from that set of functions. But in order for us to practically work with those, we assume that these functions are parameterized through parameter vectors theta. And in reality, if we, for example, learn which is the best function, we learn with these associated parameter vectors. And we specify our risk function in terms of these. And we don't really directly learn with the function. We don't directly work with the function. And this is something I want to do now here in this lecture unit, and this is what, in a certain sense, Gaussian processes are all about. So I want to do this posterior Bayesian learning for complete direct function objects, and still be able to, well, I want to do exactly that. I want to do Bayesian inference on function spaces. So first of all, before I can even start doing that, I have to now specify how distributions over functions look like from a mathematical perspective. So that's kind of us defining how or discussing how we can specify these prior distributions for a very, very large amount of the time. So I'll need quite a few slides to be able to do this. Because I'm assuming that most of you have not seen something like this before. So you know how to work with vectors and distributions over vectors, but you probably don't know how to work with distributions over functions. So let's start with some rough intuition how that should look and feel like. So I want to be able to specify a distribution over a function set so I can sample from that. So practically, let's, for example, assume that we have a certain input domain, so that we have to fix before. So I, for example, only want to work with an one-dimensional input domain, and that one-dimensional input domain should go from -2 to +2. And I now want to be able to sample functions from a random sampler from this probability distribution and plot them. And this might look like this, right? Now, of course, I don't want to only be able to sample from my prior distribution. I also want to be able to take training data into account. So assume we are allowed to see only exactly one training data point. And make a further assumption that I'm pretty sure that the measurement at that training data point is absolutely exact. So there's no measurement error at all going on. So in a certain sense, I now want to create functions which interpolate this data point exactly. And later on, I will get rid of that assumption and show you also how to use GPs properly for regression, where there is an assumed measurement error. But for now, let's assume that we want to interpolate these points because there is no measurement error. What that means to me is that I now want to only sample functions from the function distribution which are perfectly consistent with my data. So that means they should pass exactly through this point. And if there's a second observation, I want, of course, my functions to be consistent with that too. And here's a third point and a fourth one. And you can see, after observing more and more data points, the variance of my function, the variety of functions which are consistent with all of my data points shrinks more and more. And I guess we can kind of agree that it would be interesting to now define something like a mean function, right? That lies here at the center of this function distribution and goes through my points. And we could potentially also talk about something like variance of functions, right? How can we mathematically specify how this works through exact formulas and an exact mathematical specification? Let's now really define how we can work with distributions over functions. Well, actually, I'm not really going to do that immediately because that's somewhat difficult. I still want to work with finite dimensional vectors because we are so used to them. So or in a certain sense, I will only consider certain simplified functions now. So as you all know, if you have a function, and I will only consider real valued functions, that these functions, they all have an input domain, right? And for now, I only want to work with finite sets for my input domain. And in a certain sense, you could see these finite points here at like measurement points, where I'm allowed to kind of measure and see my function, and I'm not allowed to see them at all of the other points, okay? And since such a finite set, such a finite element domain has only n elements, I can represent my function h compactly now as an n-dimensional vector. So in a certain sense, vectors and these functions with finite element domains are completely the same thing. And they actually are from a mathematical viewpoint. So I can compactly write them like this. So I have my finite set of domain points x1 to xn. And there's a reason why I'm already writing them like they look like for a training set observations for a machine learning model. And the only thing that's now of interest to me to specify my function, if that input domain here is fixed, is how do the outcomes of my function h look like. So I put them all here into this nice little vector. I can now work with this vector as a representation of my function. Let's visualize this to make this even clearer. So let's assume that my input domain is from R1 and that the two finite points at which I'm allowed to measure my function are just 0 and 1. Now, how do functions look like on this finite element domain? Well, they look like this, right? So you have a vector of 2 points. So you have a vector that specifies the height of my function here at x equals 0. And the second component specifies the height here. This is another candidate function. This is a function. And this is a function. And of course, it doesn't really feel like a function, right? It's a super discrete object with just 2 measurement points. So how about we use 5 points now? We use 5 points here on our interval from 0 to 1. Now function is a 5-dimensional vector and looks like this. How about 10 points? Looks like this, right? And I guess you can see that the more and more I make this set of measurement points fine-grained, the larger I make this for this given interval, the more the resulting object, which is still finite dimensional, feels really like a function. And we kind of make this a limiting process where we use more and more and more and more fine-grained points here on this x interval, the more it seems to be really appropriate to at least see this as an approximation of a function. And this is exactly what we want to do in order for us to specify what a Gaussian process really is. But let's not do this for now. Let's stay with these vectors and talk about distributions over such function spaces. So how can we now do that? How can we specify a probability distribution over such function spaces? Well, that's super simple because the function is simply now represented by this finite dimensional outcome vector. And the only thing that interests us now is to specify how this vector here randomly behaves and to specify a distribution on such a vector. And we know how that works, right? I mean, we know how multi-dimensional random variables work. And if we want to pick a simple and super convenient distribution for such a random vector, how about using a simple multi-dimensional Gaussian, n-dimensional Gaussian? And this is exactly what I want to do. And I want to always use a Gaussian distribution over such a vector. I will make a simplifying assumption that, if I'm using a Gaussian as a distribution, I know that the Gaussian is completely specified by me knowing its mean vector and me knowing its covariance matrix K. I will assume that this mean vector here for now is always 0, and you will later see why this is not a large restriction. For now, just give me some rope. Let's always use a mean vector here. And I will also assume that this mean vector and that this covariance matrix are completely pre-specified. I know them. And we will later see how they can be chosen and also estimated. Okay, let's continue our visual example. So again, we use our simple interval here from 0 to 1 in our one-dimensional input space, and everything is still finite dimensional, and we started out by using simply 2 measurement points. I now want to specify my distribution over this function space through this Gaussian, where I'm really using this 0 mean vector now, and where I'm pre-specifying this covariance structure for capital K. And I'm visualizing this 2D Gaussian now here on the right-hand side. And then I want to sample from that. In order for me to sample functions, which I'm now visualizing on the left-hand side. So maybe I'm sampling this orange point here. So this orange point has a component h1 and it has a component h2. What do h1 and h2 represent? Well, h1 is simply the outcome at my measurement point 0, and h2 is the outcome at my measurement point x equals 1. And I can sample a different point and a different point and a different point, and I can see how these functions now look like. I can also do this for 5 points now, to have a more fine-grained resolution here on my input interval. In this case, now it's a little bit difficult or nearly impossible for me to visualize how this 5D Gaussian distribution looks like that I have to put on this 5-dimensional vector. So I've chosen now to only visualize how the covariance matrix looks like by visualizing it through this matrix here of gray values, where a point is pretty highly correlated with its next neighbor and a little bit less correlated with its second neighbor and even less correlated with its fourth neighbor and so on. And from this covariance matrix, again, I can now sample functions and you can see how these look like and feel. Or we can do this with 10 points with a similar covariance matrix structure, again, sampling points. And again, you can see how that feels. What is the role of this covariance matrix? So I want to pretty quickly talk about generating functions for such a covariance matrix. And these covariance functions, they kind of induce my covariance matrix. But let's just talk about how different structures of such a covariance matrix influence the shape and the mathematical properties of the functions that I'm sampling from such a covariance function. So I guess you might have already seen this in the last example, or might have guessed that. So here are 2 very extreme cases of me in situation A specifying a covariance function K, which where all of the values are super highly correlated to each other. Yeah? So I'm putting a 0.99 in every entry. That means that the outcome of each point is super highly correlated with the outcome of its next neighbor or of its second or third or 10th neighbor. They are all super highly correlated. And there's a second extreme case where my covariance matrix K is simply the identity matrix, so everything is pretty much uncorrelated. And what that means for A is that all of the functions I'm sampling from such a covariance structure are super smooth and they are super flat. And if I reduce this correlation structure here, if I make this less and less, the function will become more and more wiggly and rough. For this extreme case where everything is uncorrelated, I'm not even sure whether I would really call that a function. I'm basically seeing uncorrelated white noise here. And as I've said, let's try to kind of abstract a little bit away from this. What does this really mean? So I can now characterize on numeric spaces X functions through a certain spatial property. So I can say that 2 points, or if 2 points x, y, and xj are very close in terms of their Euclidean distance, or close in terms of any type of distance metric, then close in terms of a certain distance metric, their function values f of xi and f of xj should also be closely related in y space. That's kind of a continuity property, right? So, or a smoothness property of my function. And we can enforce this spatial property by choosing a covariance structure. I haven't really defined what covariance function is, but we can enforce that by choosing a covariance structure where the entry of my capital K matrix at position ij is high if xi and xj are very close together in numeric input space. And in general, for Gaussian processes, I want to be a little bit, lazy in the sense of that I don't want to really write down and completely specify large covariance matrices. What I do want to do is I want to specify this covariance matrix through a covariance function, and I want to specify and model this spatial correlation by specifying a certain covariance function. So a covariance function mathematically is a 2-argument function of xi and xj, or you can also say x and x dash, and it induces my covariance matrix by me simply plugging in all pairs xi and xj on all of the points that I'm interested in. So for my complete finite element domain, for example, and then we get this covariance function induced and defined, this covariance matrix induced and defined through this covariance function here. And here is one super popular example. This is what we often call the squared exponential covariance function, or some people also call that the Gaussian covariance function. And this has exactly this spatial property going on. Yeah? So the function here says, it has this exponential component here, and then on the inside of that, it mainly depends on the distance between xi and xj, and you can either do this on a one-dimensional domain by computing here this absolute distance between xi and xj, and if you're working on a multi-dimensional domain, you could also use the Euclidean distance here. And what that really tells you is that points that are very, very close together here on the real line, that have a very small distance to each other, they are highly correlated in terms of outcome, and this correlation drops down in an exponential manner if distances between points become less and less close to each other, And then also their relationship in terms of outcomes nearly vanishes and goes down quickly to zero, and they become nearly uncorrelated over long distances. But over small distances, they are very highly correlated. And again here, I'm now visualizing this scenario C. I'm visualizing the scenario B with this capital K equals the identity matrix, so this uncorrelated white noise. And here I'm using now this specific spatial correlation with my squared exponential covariance function. And you can see if I use that to induce my kernel matrix for 50 points in my input domain, the resulting functions that I sample from this distribution, they look reasonably smooth. And you can also see, because I'm already using 50 points, that really begins to feel like a smooth function, right? Okay, a little note on terminology. Some people also call it, including me, some people call this covariance function, and sometimes also kernel or covariance kernel. And the reason is these guys here are closely related to kernels in machine learning kernel methods like support vector machines. So support vector machines and Gaussian processes are actually very closely related models, but I don't want to discuss this now. Okay, so until now, we have pretended that our input domain here only consists of a finite number of points, and therefore the only thing for us to stochastically work with random variables of such functions is that we need to be able to work with random finite dimensional vectors. And we have specified the distribution over these finite dimensional random vectors as Gaussians with a mean vector and a covariance matrix K. Now what we want to do is we kind of want to take that to the limit and see what happens then. So use more and more measurement points, take that to the limit, and specify the Gaussian process as kind of the limit of that. So in a certain sense, we want to become as granular as we want on these input spaces. The good thing is, no matter how large n is, we are still considering functions over a discrete domain. And that's kind of the whole trick. So intuitively, a function drawn from a Gaussian process, we can kind of understand this as an infinite, as a Gaussian random vector of infinite length. But I guess for nearly all of you, it's very unclear how to handle such infinitely long Gaussian random vectors. And the good news is we don't have to do this for any interesting computation on such a Gaussian process. So at the end, it will still all boil down to finite dimensional linear algebra. So what we will require now, or what we want to have as an intuition, semi-formal intuition, is that for any finite set of inputs from our infinite dimensional domain, okay, we'll now make this domain X here infinite, of infinite size, not infinite dimensional, of infinite size. So what you should envision here as X now is, if you want to keep it simple, envision the real line. If you really want to make it like Gaussian processes for machine learning, envision R to the P, a P-dimensional input space, okay? Whenever I consider and look at a finite subset of capital X, and then consider the vector of outcomes on that finite subset, I want that this vector of outcomes, whatever the size it is, as long as it's of finite size, that this should be normally distributed. And this property we call the marginalization property of a Gaussian process. So what we want is that whenever we look at these finite dimensional input points, we can basically work, in order to kind of model the outcomes, we can work with finite dimensional Gaussians. So if you want to keep this short, you can say that a Gaussian process is defined by the fundamental property that every finite dimensional marginal distribution is Gaussian. So for example, we can now sample functions at arbitrary measurement points. So here I'm sampling a function at 5 measurement points that are of interest to me, or I can sample at 10 points, or I can sample at 50 points, because I just have to decide, do I work with 50 points? Where do these 50 measurement points lie in my input domain? And then I know that they are normally distributed. And I also, we'll talk about this a bit later, I know what their mean value is, and I know their covariance structure. So I assume that that's kind of fixed to specify the Gaussian process. And now I know how that their vector of outcomes behaves like this normal distribution, right? So I can draw such a vector, and because that's fixed, these input measurement points, I can now draw this quote-unquote function. Okay, so let me maybe directly, I guess I did all of this, so maybe let me kind of directly go to the, well, I should have stayed with this slide here, sorry. So formally, well, I kind of already did this formal definition now. So we now want to say that a function f is generated by a Gaussian process. GP, m of x, k of x, and x dash. If for any finite set of inputs, x1 to xn, the associated vector of function values, bold f, has a Gaussian distribution where this m here is the mean vector and this capital K matrix here is the covariance matrix. And these guys are computed and specified by these two functions, by the mean function m and by the covariance function k, and I assume these to be part of the definition of my Gaussian process, so they are given. So I, kind of as a modeler, I have to decide these. They fix my Gaussian process. And the mathematics behind GPs tells me that this is a valid thing to do, and that this completely specifies my Gaussian process. So you can now discuss two scenarios here. So one scenario is the scenario that we have discussed now multiple times. So ad nauseam, we have discussed here this scenario where we are only working with a finite set of input measurement points where we want to draw, for example, our function, visualize it, or because we kind of have a finite set of training data points available to us. And I mean, this definition here directly tells you that this is normally distributed with a finite dimensional Gaussian, and you can work with that. And we know how that works and how that feels. So this is not a problem. The other thing is you can now complain that, well, you still haven't told us how to work with infinite, with complete functions, or whether this definition here from a mathematical viewpoint is well defined, and that it also defines all functions of infinite dimensional sets of inputs, or sorry, infinite size sets of inputs. And there's two answers to this. So the first answer is kind of from a practical perspective, and that is that infinite size stuff doesn't matter at all anyway, because at the end we want to work on a computer and there we have to work with finite element sets anyway. Or if we work with training data, if we work with test data in the machine learning scenario, that's all finite sets. So from a practical perspective, we could say that doesn't matter anyway. Who needs to work on infinite size sets? sets of infinite size. From a mathematically formal perspective, it's also valid because, and this is something I cannot prove here, if you use this marginalization property and pick your definition of a Gaussian process exactly as I've done it here, that every finite dimensional marginal distribution is Gaussian and that it's defined through a given mean function and a given covariance function, we know that this fixes the Gaussian process and the distribution over all functions completely. So there is no gap in the definition. Every stochastic property of the complete GP, even on infinite, even on sets of inputs of infinite size, everything is fixed and defined by this finite dimensional marginal fixing of things. This is something that's pretty hard to prove, and I will not do this here at all, but I just want to mention that fact so that everything is also well and okay and nice from a formal perspective. So I want to add a few more comments on this mean function and on this covariance function. So the mean function and the covariance function, what they formally specify. So the mean function is basically me computing the expectation over such a random function f of x at every point x, and that's the formal definition of the mean function. And the covariance function here is me computing the covariance at a certain measurement point x and a certain other measurement point x dash through the normal covariance formula. For now, we will always assume that this m function is completely zero. So we will call that a zero mean Gaussian process, and we'll later on see that this is actually not a drastic limitation. We can use and we can work with non-zero GPs, and that gives us a certain flexibility, but that's not necessarily even needed. The covariance function, on the other hand, this is something that we as modelers have to specify and pick. So, for example, we can say we like this spatial smoothness that we talked about before, and we have already seen that this is kind of induced by this squared exponential covariance function. So we might pick a function like that, and we could, for example, parameterize that at least a little bit by putting here an L squared in front of things. I've used L equals to 1 before. And this is something that I have to pick as a modeler. This is kind of where the flexibility, where I have flexibility in specifying how my Gaussian process should feel like, what properties it should have. I'll discuss this in a later lecture unit. I just wanted to make it concrete here to give you one concrete example. So if you like this spatial smoothness property, you could, for example, pick such a squared exponential. And I want to mention one other thing before. So there's like good news and bad news about this covariance function. So bad news is we have to pick it as a modeler, so that shifts some burden on us. There's also good news, and this is, you can already see me entering here or using hyperparameters, right, in this squared exponential function. Usually in all other machine learning models, I now have to do parameter tuning to figure out how these hyperparameters should be set. For a Gaussian process, I can directly learn these hyperparameters during the training process, so they become data optimal. And this is one of the super, super nice properties of Gaussian processes. So how can we now put this principle to work? So if we want to sample now from a Gaussian process prior, we can choose, for visualization purposes, a super high number of, for example, equidistant points x1 to xn. Now, because we want to visualize this on a computer, right? So if we want to plot this, it's going to be, like I said, a finite number of points anyway that we visualize the function on. Now, we enter all pairs of points into our covariance kernel K. So we put all of these xi's and xj's, for example, x1 x1 and x2 and x1 and x3 and x5 and x7 into our covariance function, and by doing that we compute our covariance matrix capital K. Now we know that the outcome vector of our GP function on this finite set of points is described by this Gaussian here. So we just draw from that Gaussian now and we visualize it. And if n is super large, so if this is I don't know, 500 points on this interval here from -2 to +2, that really now feels like a true function, right? Although in the background, everything, like every computation and every mathematical operation basically was boiled down and reduced to finite dimensional linear algebra. Actually simple finite dimensional linear algebra, because we're only working with Gaussians here. And as I've said before, my usual default is to use a zero mean Gaussian process. So this m here is the zero function, which also means that if I compute the mean of all of these sampled functions, this will be located at 0. Some final comments about Gaussian processes as an indexed family, and to connect them a bit more with stochastic processes. So a Gaussian process is a special case of a stochastic process, and as you may or may not know, a stochastic process is defined as a collection of random variables, usually a dependent collection of random variables, which are indexed by some index set. And we sometimes also call that an indexed family in maths. What does that mean? So an indexed family is nothing too complicated. It's fancy terminology for, hey, we have an index and that tells us to pick a certain element out of a set. So we define a family of elements of an index set S indexed by some index set T, and we call that an indexed family, as a surjective function, where we have a surjective function S here that takes an index and that goes to S. What that only means is that if you specify an index, the indexed family tells you or which element you're referencing, okay? That this is a well-defined operation. So if you pick an index, it's not allowed that no element is referenced by this or that two elements are referenced by this. And what I want to make clear through this super formal discussion of things is that an index is basically nothing more than the computation of a function by an argument. Okay, so you could also write this as S of t as a function argument. And here are some well-known examples of index families, and I will start with pretty trivial stuff that you hopefully recognize again. So how about we use an index set that's just one. That's just a finite bunch of numbers, goes from 1 to 2 to n. So visually the index set looks like this, super simple. And how does this S set now feels like? Well, it feels like a list or a vector, right, of finite length. And if we now talk about if these guys are now dependent random variables, well, what is this here? Well, that's just a random multi-dimensional vector, right? And you know how to work with this. So you know such objects. What if we have an infinite index set? For example, t equals the set of natural numbers. Now the index set looks like this. 1, 2, 3, 4, 5 until infinity. And we have now a sequence of infinite length. And we can now talk about random distributions over such infinite sequences. And you might have done this before, maybe not. So, for example, I already said if t is finite, that's just a random vector. If you could also see this as a stochastic process in discrete time. If t is such a sequence of natural numbers, another interesting stochastic object, for example, would be a random walk, right? So where you maybe move from one point here to the next, to the left-hand side or to the right-hand side. We can even do this in 2D discrete space. So where T is the set of two-dimensional integers, and now we have a random walk that moves over the plane here in discrete steps. What I mainly want to discuss in the context of Gaussian processes, is that this index set is actually the real line or R to the P. So it's either the real line for a simple case where I talk about 1D functions, or when I really want to become machine learning, I really want to have X as R to the P as a P-dimensional input space. So, and the special feature now of the Gaussian process was any indexed finite random vector has a multivariate Gaussian distribution with all of the nice properties of such Gaussian distributions. So in the simple case of X being just R, you have your complete real line available to you, and these points here, your measurement points that are kind of indices of your random variables. So you have a random variable f indexed by f indexed by x, or f indexed by x tilde, and you can see if these quote unquote indices are real valued numbers, I guess you'd really rather write them here as function arguments, right? And now you know that this two-dimensional object here, this two-dimensional vector, this is just distributed as a Gaussian. This was our marginalization property. Or you can also do this on R to the 2, where P equals 2, so we have a two-dimensional input space. And again, the outcomes for these 2 points are again Gaussianly normally distributed.